So let's now talk about what makes a dependency structure well formed. That is, how do we define the set of possible dependency structures for a given sentence? And we're going to focus on two constraints which will be important. So the first constraint is that these directed arcs form a directed tree with this root symbol at the root of the tree. So this basically means that if I pick any word in the sentence, for example, movie, there's going to be a directed path from the root to that word. So in this case, the path is first this arc root to soar, and then this arc soar to movie. So every one of these words is connected to the root through a directed path. And this structure, in addition, forms a tree, which means, for example, there are no cycles in these paths. We have no cycles like this. The second constraint, which we'll come back to in some detail in a second, is that there are no crossing dependencies in these structures. So crossing dependencies would look like the following. If I have a structure like this, say this is the root, and these are the four words in the sentence, you can see that these two dependencies actually cross. And so in this definition I'm going to use in this lecture, we're going to rule out these kind of structures. I'll talk more about this in a second. So if we come back to this simple example, John saw Mary, there are actually 1, 2, 3, 4, 5 possible dependency structures in this case. 5 structures that satisfy those two constraints that I just showed you. The correct one is here, but of course there are these 4 incorrect structures for this particular sentence. So the parsing problem is essentially going to correspond to searching through these different possible structures and finding the one which is most likely or most plausible under some model. Let me just talk a little bit more about these crossing dependencies. So what I've shown you here is a dependency parse structure which does have one of these crossing dependencies. So notice here we have a crossing dependency. Structures which allow these crossing dependencies are often referred to as non-projective structures. And they can actually be useful in some scenarios, and depending on the language and the constructions involved, you can actually see these kind of non-projective structures. Here's an example from English where arguably the correct dependency parse certainly does have a crossing dependency. For the purposes of this lecture, we're going to assume that these structures are not allowed, so they're not in the space of possible dependency structures for a particular sentence. And that's a pretty good approximation for a language like English. Right at the very end of the lecture, I'll talk a little bit more about extensions to these models which do allow structures of this case. But for now, assume these structures are ill-formed. So there's been considerable interest over the last few years in dependency parsing. You'll see later in this lecture it has certain advantages in terms of efficiency and simplicity. But let me talk a little bit about resources. So in 2006, a conference called Connell had what was called a shared task, basically a friendly competition between different groups, where they released dependency parsing datasets for actually 12 languages. So Arabic, Chinese, Czech, Danish, Dutch, German, Japanese, Portuguese, Slovene, Spanish, Swedish, Turkish. And 19 different groups developed dependency parsing systems and compared their results on these datasets. A very similar setup was seen in Connell 2007. The approach I'll describe in today's lecture is largely based on a PhD thesis by Ryan McDonald, which introduced global linear models for dependency parsing and showed that these models were really very successful. We'll be treating this problem as a supervised learning task, so we'll assume we have training examples consisting of sentences paired with dependency structures. So this is what each training example will look like. And so there's a question of where do we get these resources from? Where do we get these dependency banks from? So there's a couple of ways that these data sets arise. For some languages, a famous example being Czech, people have actually hand-constructed dependency banks. So they have annotated large quantities of data, again maybe thousands or tens of thousands of sentences, where each sentence is annotated with its underlying dependency structure. So you can think of this as an analog to a tree bank. We had seen, for example, the Penn Wall Street Journal tree bank, where people had annotated constituency trees. In some cases, for various languages, rather than annotating these kind of constituency trees, they directly annotated these dependency structures. Now, for other languages where these dependency banks aren't directly available, we may have these constituent or tree banks, like the Penn Wall Street Journal tree bank. And you hopefully won't be surprised that it is actually fairly straightforward to extract dependency structures from tree banks. The lexicalized PCFGs that I showed you earlier in this course opened up a direct link between these constituency structures and the dependency structures we're considering in this lecture. So let me talk a little bit more about that. So here is a constituent-based tree, something like the kind of tree you would find in the Penn Wall Street Journal tree bank. And I think this is an example that we saw earlier in the course. And we've lexicalized this tree in the way I described in the lectures on lexicalized context-free grammars. So each non-terminal has an associated head word. For example, this NP is president, or this VP has was, or, sorry, this is missing. This S should also have was. This NP has she, this S bar has that. So in the same way as I showed you earlier in the course when we looked at lexicalized PCFGs, we had these rules that propagated head words up through these context-free trees. So that was a step, this lexicalization step was used in deriving lexicalized PCFGs. But it also opens up the chance of taking these tree structures and converting them to dependency structures. So remember, each dependency can be represented as a pair, HM, where H is the index of a head word and M is the index of a modifier word. And so in this particular case, this example tree is going to be converted to the following set of dependencies. Let me give you an example. So with this rule, S told goes to NP Hillary, VP told, we can extract a dependency where told is the head and Hillary is the modifier. So that gives me this dependency here, 2-1. We have a directed arc from told to Hillary. Similarly, if we look at this rule here, we have told as the head and Clinton as a modifier. And so I have an arc 2-3. So I'll number these words 1, 2, 3, 4, 5, 6, 7. I have an arc 2-3 from told to Clinton. And similarly, I have an arc from told to that, 2-4, because I have that also as a modifier to told. And we can similarly go through the entire tree, pulling out all of the dependencies. Right at the top of this tree, we have told as the root of the entire sentence. And because of that, we have an arc 0 to root goes to told. So, to summarize, the main point of this slide was that if we have a tree bank, that is a set of sentences with annotated context-free trees, we can convert this to a so-called dependency bank. And this step is through lexicalization. Exactly the step of lexicalization we saw within the context of lexicalized PCFGs. And once we've done this, we have training and test data for the dependency parsing problem. So one very interesting property of dependency parsing, and a compelling reason for taking dependency parsing very seriously, is the efficiency with which we can find these dependency parsing structures. So when we looked at probabilistic context-free grammars, we saw this dynamic programming algorithm, the CKY algorithm. And it had a runtime which was cubic in the length of the sentence, and also cubic in the number of non-terminals in the grammar. So n might, for example, be 20 or 30 or 40. The number of non-terminals might be, depending on how you define it, 10 or 20 or 50. Again, some reasonably large number. And this is quite challenging. This is actually a pretty large number, and you can see that this g cubed term can certainly lead to problems in terms of efficiency. Lexicalized PCFG parsing is, at least under the methods we saw, n to the fifth, where n is the length of the sentence, and again cubic in the number of non-terminals in the grammar. So this is really getting very expensive. Algorithms for unlabeled dependency parsing, again, are generally based on dynamic programming. We're not going to see these in detail because they're fairly complex and it would take some time to go over them. I'll post the references. But there are some rather beautiful algorithms for dynamic programming over dependency parsing structures, in particular due to Jason Eisner. I'll post the papers. Remarkably, these algorithms are cubic in the length of the sentence, but have no dependence on the size of the grammar. In fact, in some sense, dependency grammars don't really have non-terminals, so they don't really have these G terms. So there might be a small constant in front of this n cubed, maybe a factor of 8 or something like this, but a constant that is way, way smaller than G cubed. And that actually means that these dependency parsing algorithms are, in practice, extremely efficient. And that is a major reason for, like I said, taking dependency parsing very seriously. So it has two properties which I think are very beneficial. So they're very efficient parsing. Secondly, they are very useful representations. So if we can recover these kind of dependency structures, they're useful in many applications in natural language processing.